Thank you. So the goal of this talk is not to advertise another modeling language. It's hopefully to be able to take some of the ideas that were successful in Gravity and maybe include them in JuMP at some point so it becomes more efficient. So before I dive into the ideas that worked, I want to share the backstory of how I started working on Gravity, why I decided to build this modeling language. So it all started with STPs. This was 5 years ago. I was starting to look at the optimal power flow problem. And you heard this morning, it's a non-convex problem. You can have natural, tight, semi-definite programming relaxations. And so the problem was that STP solvers were still slow, not very scalable. And what I was trying to do in my research is scale these semi-definite programming formulations or find an alternative way of solving these formulations other than calling an STP solver. Ideally, generate guts like we do in mixed integer linear programming to capture what the PSD matrix is actually capturing. If it's not linear, I would be happy if it was nonlinear at the beginning. So I will show you in this talk the nonlinear cut generation approach. And to be able to get to this, those cuts, I'm going to use this characterization of PSD matrices, one of the different characterization that says a matrix is PSD if and only if all its principal minors are non-negative. Now the principal minor is simply the determinant of a submatrix of your given matrix, where you remove a set of columns and a set of rows from your matrix, and then you look at the determinant and it has to be non-negative. So I'm going to go through this simple 3x3 example to see what those determinant constraints look like. So I'm going to start with k equals 1. I'm allowed to remove 2 columns and 2 constraints. And I can do this in 3 different ways on this 3x3 matrix. And at each time, I only get 1 element left. The submatrix here is just the diagonal element, and it has to be non-negative. So the first set of constraints is saying that the diagonal elements have to be non-negative. For k equals 2, now I'm allowed to remove only 1 row and the corresponding column. And when I do that, I get 2 by 2 submatrices. And this gives me this nice rotated second order cone constraint that you can see here. This thing. And I get 3 of them depending on which row and which column I pick. And finally, for k equals 3, I'm not allowed to remove any rows or any columns, and I need to look at the determinant of the whole matrix. Okay? And this is one way of writing the determinant. You can write it in a different way depending on which column you fix. And then if you look at this constraint, it is actually non-convex in the x variables. But the beauty of this is that the intersection of all these constraints is strictly equivalent to saying that the X matrix is PSD, which we know is a convex set. So, email sent. So the intersection of these constraints will define a convex region. And to give you some geometric intuition, I have some nice pictures. What I did here, since this is a 6-dimensional matrix, I fixed the diagonal elements to be 1, and then I represented the feasible region defined by the 3x3 determinant constraint, which here is the points inside this object in the middle and inside the cones in every corner. So it is a non-convex feasible region, But if you intersect it with the 2x2 minors, which are, the second order cone constraint we saw, in this space, those constraints are linear, and you get these hyperplanes, and they are telling you that you need to be in the middle. So the only visible region left is this thing called an elliptope, which you cannot see here. I had a nice, this was supposed to be moving, but I had to use PDF. So the visible region, or this is, you can think of it as the projection of what a PSD constraint is into this space. So my goal was, the catch here is that you have an exponential number of these determinant constraint. The exponent being the size of the matrix you want to be PSD. So my first thought was, can we do this in a lazy fashion? Not all of them are going to be active. Hopefully, if we just add a subset, it will be sufficient to capture the PSD condition. So my goal was to efficiently implement a lazy constraint generation of these polynomial constraints. Now, these are non-convex constraints, and I wanted an efficient modeling language to deal with that. At the time, I wanted something open source, something that doesn't write NL files for every model you want to solve, because I'm going to solve this iteratively every time I'm going to generate new cuts. So JuMP was a great, candidate. It was so nimble, the only nimble and agile framework. The only issues, I had few issues. One of them is highlighted in this screenshot, which is basically saying, the AD in Julia, I don't think it's JuMP's fault, it's the AD in Julia can be, you're finger pointing, is just not as good as, Ample's AD or other commercial. And unfortunately for the ACOPF, it hits that bound. The function evaluation is 5 times slower, which means if you solve the polar formulation, you're going to be 3 times slower for exactly the same model. I also was more ambitious in what a modeling language should do. I wanted a lot of things out of the modeling layer, like being able to detect convexity of sub-expressions, for example. Lazy constraint generation was, of course, something I wanted to have, even on nonlinear constraints. So I would ideally want to tag a constraint saying, look, this is lazy, you only add the instances that are violated, not all of them from the beginning. And, other properties. So I decided, okay, maybe I'll give it a try, see if I can do all this. And I said, let there be gravity, and gravity was. And so the main thing that gravity exploits is structure, okay? In optimization, in machine learning, we don't solve random problems. The problems we solve have a lot of structure, and the key, there's no free lunch. The key of being fast, efficient, is to exploit that structure. So gravity exploits structure in 3 different ways. I'm going to go through these three things. First, start with template constraint. The idea behind template constraint is quite simple. If you have a lot of constraints that look, similar at the backbone level, the only thing changing is the constants and the right-hand side. You don't want the user to write a for loop, and you don't want to build the expression for 10,000 copies of the same symbolic constraint. So ideally, you want something like this, where this is what I call a template constraint, where you just define it once, and then and the modeling layer should do the indexing underneath. So it won't build the structure, the expression tree for every copy. It will only do it once. This is also useful because you can do convexity analysis at the symbolic layer. In this specific example, I can immediately guess that regardless of what the constants and the right-hand sides are, all the copies of this constraint are going to be convex. And I don't have to go through each one of them. I can do this on the symbolic layer. Another interesting thing is I can also do symbolic differentiation if I have compact formulations at the symbolic layer using template constraints. Then I don't need to go through AD. Maybe SD is going to be as efficient. And we're going to talk about this. So before I go into differentiation, I wanted to see if even before calling the solver, all these tricks would help in building the model, because there's a cost of building the model. RTE was saying that it needs 5 minutes to build the layer hierarchies. That's not something ideal. So here so Julie talked about the ACOPF. This is the one formulation of the ACOPF. It's a lifted version where I've replaced every product by a new variable W. So these are the real part of the product, imaginary part. These are my power flow constraints. They are linear in this lifted space. These are my power flow conservation constraints. Everything that comes in comes out. This is also linear. These are my thermal limits on the line, so you can think of them as capacity constraints on the edges. And then this is the non-convex constraint that links the lifted variables between each others. And so if you add this constraint, this is strictly equivalent to the non-convex ACOPF. And so what I did is I formulated both the polar formulation and the rectangular formulation in Gravity and JuMP, and tried to see if these tricks, in terms of template constraints, help the build time. So what you see here is pglib instances. There's 113 instances times 2 because I'm looking at the polar and the rectangular formulation. So one formulation has trigonometric functions. One is purely quadratic, non-convex. And what you see here is the time just to build the model even before calling the solver. So this extreme case here on the left, this maybe you can't see it, but it's a green bar saying that JuMP took 9 seconds almost to build the model, and IPOpt needed only 30 seconds to solve it. So this is the kind of things we would like to avoid ideally. So these template constraints help. It would be great if at some point we can have them in JuMP too. The third thing, this is the second thing that I'm exploiting in Gravity, is the way Gravity looks at functions. If you look at any state-of-the-art modeling language or solvers, they will have expression trees to store the constraint structure. So they will have these directed acyclic graphs to represent what the function is. Gravity has a different view where I basically split the linear part from the quadratic part, from the polynomial part, and only then, if you have some weird functions like log or square root or exponential, only then I build the expression tree and put these in there. So this also helps, again, for the same reasons I mentioned before. You can do convexity detection at the symbolic layer if you have, if you know that E of x is empty, then you can do a better job in looking at the convexity. Same for differentiating the function. Third thing is what I mentioned before about symbolic differentiation. You open any book about the subject or read any paper, you will find this argument that symbolic is not good because the expression tree can quickly become exponential when you derivate symbolically. And the first paper I found was a math prog paper by 89, and it presents this argument. So the keyword here, in my opinion, is careless. Okay? And the question I want to answer is, can we perhaps be careful? And how much does it cost to be careful? Is it something that requires complex data structures or not. So to give you an illustration of what I'm talking about, I'm going to take this very simple nonlinear expression. Here A and B are constant parameters. My variables are x and y. And you can see that this expression depends on different expressions. It depends on cosine being multiplied with A divided by B. So I'm not putting the operators here, but there are operators linking all these expressions together. And let's say I want to differentiate this expression with respect to x. This is what the derivative looks like. And you can immediately see that this expression will share at least this atomic function, this linear function, with the original function. So if I'm not careful, indeed, I will duplicate these computation. If I do it, if I just store them separately, then I will have to compute x minus y twice if I'm calling, evaluate function and evaluate derivative. This is a simple example. It can get even worse, in practice. And so if we're just using simple maps and queues, which I did, I implemented, I used maps to be able to avoid duplication in my symbolic expressions, and then queues to make sure that I'm evaluating the functions, from bottom up, not doing a big function before a small function. And so that's what I do. And it really works in practice. I was surprised to see that it actually works. So here I'm presenting the exact same 216 instances of ACOPF. You have the quadratic and the nonlinear formulations. So this is a performance profile showing the percentage of instances solved with respect to time and on this axis, log scale of time, comparing gravity, JuMP, and then there's the ample NL writer in Julia. So you can write the model in JuMP and then write an ample output file. And so you can see here what I'm highlighting is that for the polar formulation, Julia's AD is not as good as Ample's AD, and you can see that Ample is doing a better job. But then for the rectangular formulation, JuMP doesn't use, I believe, Julia's AD. It has its own, it recognizes that it's a QP, and it doesn't need to call the AD, and this is where it becomes much more efficient than Ample. One nice fact is that I also tried to solve these instances with a dedicated ACOPF solver. It's called MatPower, and so this is just a solver that solves ACOPF, and it was failing on some of the instances, and it was slower than Gravity on other instances. To give you an idea of the size of the problems, the biggest problem here has 100,000 variables, 200,000 constraints, and a lot of non-zeros in the Jacobian and the Hessians. Another problem that I looked at comes from machine learning, where again, there's a lot of structure in the formulation. The only thing that is the bottleneck is the parameter or the input size. So you have a sum, which is this sum here, that has 92 million non-zeros. Okay, so the function is simple, but once you expand it, it's huge. And so I implemented this again in Gravity JuMP, used the ample NL writer. And it turns out, I'm not sure which part or which trick was helping the memory to be efficient, maybe the template constraint or the symbolic differentiation. It was able to solve all of the instances. So this is in growing size of input parameters. Ample crashes very quickly because it's writing an NL file on the disk. JuMP, I'm not sure what's happening. And so what does it look like? I'm just showing some simple formulations here. I guess it looks a bit like JuMP, where you declare variables, you add them, you declare constraints, you add them, you choose a solver, you run. These are some of the ACOPF constraints. This is the power flow conservation. One nice feature that we might want to, at some point consider in JuMP is it's graph aware. So if you declare a graph, you can index based on the edges of the graphs or the nodes of the graph. You say, for all nodes or arcs. One thing I also wanted to have in there easy to run is if you have a set of subproblems, you want to be able to run them multi-threaded. And so I created this simple function where if you create a vector and then you start adding models to there, I'm supposing that you already build these models up there, and then you say run parallel, you specify the number of threads, it does that, and in parallel. I think we can also do simple things in Julia like that. Of course, the lazy cut generation, I was also able to do that in a simple fashion where this is the phase angle bound constraints in the ACOPF. It's just a simple linear constraint. It's indexed on the set of bus pairs. If you say add, it will add all of the constraints on all of the buses, all of the bus pairs. And if you just say lazy, it will iteratively solve your problem, check if any constraint is violated, and then add them dynamically. All right. Now the interesting part is the SDP cuts, because I did all of this to get to this point where I could implement those determinant cuts and see how they perform in practice. So this is a table showing some of the hard instances of ACOPF. So I've removed all the instances where the second order cone relaxation was already closing the gap. And I've implemented the full SDP relaxation and linked it to MOSEC. Then I implemented the sparse SDP, which corresponds to doing the chordal extension and decomposing the big SDP into smaller SDPs. So that should be much more scalable, hopefully. And then there's this dedicated ACOPF SDP solver that relies on a tweaked version of SDP-D3 by the Berkeley group. And so I'm comparing here. When you see red, it means it either ran out of memory or it says I didn't converge. And so you can see these, and here, oh, sorry, I forgot to mention, I'm only adding the 3x3 determined constraints. So even though in theory, you would need exponential number of these determined constraints, what I do is after I do the decomposition, I now have cliques in my graph. And the theorem, the matrix completion theorem says, if you apply SDPs only on the cliques, this is strictly equivalent to saying the whole matrix is SDP, which is great. You have smaller cliques, smaller matrices. So what I do is I look at these bags of nodes, which represent my cliques, and then I decompose them into bags of size 3. So if I have a clique of size 4, I'll have many cliques of size 3. And so I add the determinant constraints corresponding to these 3x3 matrices. And what you can see here is the gap is actually SDP. Okay, so I have like a 1% accuracy. So if it's between, if it's less than, the difference is less than 1%, it's due to my stopping criteria. So it's matching the full SDP constraint. And I'm solving this using IPOpt, okay? And so if IPOpt converges and says, well, this is a KKT point, since the feasible region is convex, it's a guarantee that I'm at the global optimal solution. So all I need is call IPOpt. So it's working pretty well. I was really happy with this. So this decomposition into 3x3 matrices is a recent thing I tried. And so I didn't have more experiments. And yesterday at 3 a.m., I woke up because I'm still jet lagged. And I said, let's try this on bigger instances. I know they have these Polish RTE instances. So I wanted to try on the hard ones. So I looked at this table. This is just showing the second order cone gap. So this is the simplest relaxation you can look at, where you only look at 2x2 minors. And what you see here is I mean, you can ignore those columns. If you look at this, This is telling you the optimality gap comparing the non-convex solution with the SDP, the second order cone relaxation. So you can see the second order cone relaxation is already quite good on some of the instances, even the big ones. But there are these outliers here. So I picked those, and I tried to see if I can improve on the second order cone relaxation gap using my SDP constraints. And so these are results from 3 a.m. this morning on my old MacBook Air that Harsha calls a crappy computer. And so, I mean, you can expect to be able to divide these numbers by 3 at least on a decent computer. But it's actually closing a good chunk of the SOCP gap. And my guess is that this is actually what you would get if you would call an SDP solver. And it's not taking an insane amount of time, which is good. I mean, there's still room for improvement. Okay, future work. I have a postdoc who's starting to look at automatic decomposition in gravity. One thing I'm really interested in is how do we do projections even if you have nonlinear equations, but one of the variables appear linearly in that equation. I can use that at the symbolic layer to project it out. So I express this variable as a function of the other variables in a symbolic fashion, and then I replace it everywhere it appears in the formulation. And why do I want to do that? Because it would be great to be able to express the formulation in the degrees of freedom, excluding all the auxiliary variables. So I think of equations as just defining auxiliary variables. And I don't like those. We want to get rid of those. This is very useful, for example, if you want to build inner approximations of your non-convex set, because you cannot build an inner approximation of a surface. Think of a surface being what an equation represents. How do I build an inner approximation of a surface? It's not easy. But I can easily build an inner approximation of a half space defined by a surface. So ideally, I only want inequalities. I don't want any equations. So this is something I'm trying to implement in gravity. Some long-term objectives. Los Alamos people love differential equations. Physics is all about differential equations. So maybe we can try looking at that. There's a lot of work to be done on uncertainty, stochastic, robust optimization, and maybe at some point merge with JuMP. I was trying to come up with fun names. Anyway, thanks. That was everything I had to say.